integration method, right, we need to find the function of the slope, right? And then we have to integrate twice. But before we go there, we need to write down our boundary condition. Okay, so this is where we write out our boundary condition now. So we're going to put below boundary condition. So on the left hand side, x is equal to 0. On the right hand side, x is equal to 6. Okay, meters. So to write out the boundary condition, remember I got you all to memorize 4 uh, characters, right? V, M, theta, Y. V, M, theta, Y. And Y is at this sequence, and what do we just learn? When you find V, you integrate, you get what? You get moment. And then also today I'll teach you, and then when we apply the elastic curve from the moment equation, we integrate, we get our what? Slope. And then we integrate again, we get our what? Deflection. Okay. So for now, we only going to focus on VMM. Okay. For now, we only know our VMN, and also we know what is our Y. Y is very straightforward. So at point A, right? Point A is able to move. Yes or no? So the reaction force is equal to 0. I repeat again, point A, the reaction force of the structure is equal to 0 because it's allowed to what? It's allowed to move. Okay, it's allowed to deflect. Now, what is the moment at point A? Anyone? What is the moment at A, or when x equal to 0? It's equal to 0. Well done. Y equal to 0. Anyone?
When you integrate 0, you get 0.
Physically, what does it mean?
It means that it can't rotate because there's a support. It's actually supported with the wall.
That is opposite. It can rotate. Okay, what do I mean when m equals 0? When m equals 0, if we were to remove the support at B, what will happen? Anyone?
It would fall.
Yeah, the beam will rotate. Yes or no? That's why moment is equal to what? 0 at x equal to 0. Right? Don't memorize any of all this. You have to do by what? Understanding. I repeat again. If we remove the support at B, right, and point A is pin, okay, then the structure will start to what? Rotate. That's why moment is equal to what? 0. Okay. Now let's not talk about slope. Deflection is not equal to 0. On the right hand side, at point B, right, your V is equal to V max based on this distribution, and your moment will be at M max. What value? I don't know, but I know that it's going to be the maximum and will not equal to 0. Any idea why it's not is equal to maximum? Anyone will make a guess?
There's a counter moment there.
No. Why is it maximum? Even though it has a counter moment, but what? Yes, it's at
Because
his.
because it's fixed.
It's not just fixed, because if this thing is going to break, where is it going to break?
At the wall.
At point B. Well done. Okay, so that's why fracture. That's why the moment will be maximum. And one thing we also know that Y is equal to what? 0. That's very obvious at point B. Yes or no? Okay. So the first thing that we have to do when applying the integration method, but let's see what we're trying to achieve first. Okay, so we're going to find the shear force. Okay, we will find the shear force and bending moment equation using the integration method. Now, if you look at the integration method, okay, some of you might say, Eugene, yeah, whatever, man, dude, I can solve this without the integration method. You are absolutely right. I have no dispute with you about it. But I want to show you, okay, what are the advantages of using the integration method. That's what this is for. And when, okay, more important thing is when to use the integration method. Okay, so the integration method for this case will be the ideal case. Okay, let me show you why. So the first thing regarding the integration method, today nothing seems to be working right for me at my end. Okay, so to use the integration method, let's look at the solution procedure. Yeah, so solution procedure. So the first thing we have to do is you have to find the equation of the distributed load. So for this case, we are going to identify what is our omega as a function of x. Then after that, we're going to substitute into dv over dx is equal to minus omega as a function of x. Then after that, oh, my page ends. After that, we are going to do we're going to integrate. Let me carry on over here, okay? Oh, you know what? I'm going to start on a new page. I do apologize. Okay, so after that, we are going to integrate. Okay, we're going to integrate number one, right? So we'll have v as a function of x, okay? And then we're going to have minus omega x, right? Dx plus by c1, okay? And then this is equal to dm over dx. Now, I'm going to ask you guys a question. As I said, you guys know integration better than me, okay? With the amount of integration that you have done in math, I'll tell you this for straight. You guys know more integration than me. Now the question is this. Over here, you see a C1, right? When we were writing up the equation before, or this expression before, right? When we were writing this, you don't see any C1 at all. Any idea why? Anyone?
It's the constant we add at the end of integration.
Yeah, but why for this case, I don't need to put a plus C1?
Because we have two values which are d and c.
Yeah, because you have limits. When you have limits, you don't need the constant C1. Yes or no? Well done. I'm so proud of you guys. You guys remember what you learned in math. I'm so happy. So that's why for this case, we did not have any two values down here, did we? Right? We did not have anything. Right? So that is why you need to have a what? You need to have a constant C1. Then after that, when you have this expression, you integrate again. Okay, we integrate the second time. Now you have m as a function of x. Now we are going to integrate twice. Okay, minus omega as a function of x once, twice, plus by c1x plus by c2. Okay, so this is our solution procedure. Where c1 and now c1 and c2, right? C1 and C2 are constants are constants that are determined with the boundary condition. So what do I mean by that is we have just listed out what you can observe that we have just listed our boundary condition. If we don't know the boundary condition, this technique is as good as useless. Okay, knowing the at least one side, you have to know the boundary condition. If you don't know any of the boundary condition, we are done. Okay, so let's look at the first thing. So we want to find the equation of the distribution. So number one, we're going to find the equation of the distributed load. Okay, so this is what we're going to find. So the equation of this distributed load. So now we're going. My axes are different now. I want you to watch this. Okay. So now I have my y-axis now is my omega, right? And my x-axis now is my x. Okay, so this is my x. So we know that over here, this is 6 meters. Okay, and then our slope goes like this. So at this is 6,000, 12,000, 18,000. Okay, and the distance is 6 meters. So now we have to find, and it's real straightforward, we have to find the function of the line. Okay, so the function of the line, so omega as a function of x is equal, so the slope, right? So we're going to find the gradient. So the gradient over here, so the gradient that we're going to find, so is this distance. So from here to here, okay, so from here to here is 12,000, and from here to here, this distance from here to here, this is equal to what? 6. So it's equal to 12,000 divided by 6x plus by the y-intercept, which is equal to 6,000. Okay. So now we have omega as a function of x is equal to 2,000 x plus by 6,000. Okay. Again, this is the equation of the distributed load. So over here, our x-axis is x, our y-axis is omega, right? So this is a very simple slope. If you have a very complicated load distribution, you can use Excel. Yes or no? You can use Excel and you can do curve fitting on the second order, third order, fourth order, fifth order polynomial equation. Okay. Now, so now I'm going to call this my equation number 1. Okay. This is our equation number 1. So from equation number 1, so we're going to substitute equation number 1 into dv over dx, okay, which is equal to minus omega as a function of x, right? So from here, we know that dv over dx is equal, so it's minus what? Omega x. So this will become automatically become minus 2,000 x minus by 6,000. Okay, and next, this is the most difficult integration that we are going to use in this class. Okay, so v as a function of x is equal to minus 2,000 x squared divided by 2 minus by 6,000 x plus by c1. That's it, right? That's it. Okay, some of you like, Eugene, seriously, right? So over here, we have v as a function of x, and this